Welcome to another episode of People Pod. Today, we're taking a deep dive into just a massive stack of atmospheric research, planetary data, fluid dynamic models, basically everything we can find to unravel one of the most bizarre mysteries in our solar system.
Yeah, it's a fun one today.
It really is. And the mission for us here is to understand not just what this phenomenon is, but, the underlying physics of how something so seemingly impossible can even exist.
Right, because it really shouldn't exist. Not based on, everyday common sense anyway.
Exactly. So I want you to start by picturing something with me. Close your eyes, if you can, and imagine you're gazing straight down at the North Pole of a colossal gas giant.
Just hovering right over Saturn.
Right, you're hovering over Saturn. Now, based on everything we know about weather on Earth, or, even on other planets like Jupiter, you would naturally expect to see a massive, swirling, circular hurricane.
Yeah, just a chaotic, round maelstrom of clouds. That's what gas giants do.
But instead, as you look down through the haze, you don't see a circle at all. You see a perfect, massive, six-sided polygon.
It's wild.
It is. A flawless geometric hexagon just sitting there at the top of the world.
It is an incredible image to conjure, and I think the most stunning part is that it's entirely real. What you're describing is Saturn's hexagon.
Yeah.
It's this permanent cloud pattern situated at about 78 degrees north latitude. And to truly appreciate what we're looking at, we really have to establish the mind-bending scale of this structure.
Huge.
Oh, it's beyond huge. Each of the 6 sides of this hexagon is approximately 14,500 kilometers long.
Wow.
Yeah, for those working in miles, that's roughly 9,000 miles per straight edge.
Those numbers are so overwhelmingly huge, they almost lose their meaning, honestly. But to put that in perspective for you, the listener, the entire diameter of the Earth is about 12,700 kilometers.
Right, which means every single side of Saturn's hexagon is about 2,000 kilometers longer than the entire width of our home planet.
That is just insane to think about.
It really is. I mean, you could literally roll the Earth along one edge of this shape, like a marble on a track, and you'd still have plenty of room left over.
And it's deep, too, right?
Yeah, it's a storm system towering 300 kilometers, or nearly 190 miles high, and it's a highly dynamic system. The winds forming the perimeter of this hexagon are tearing around it at 320 kilometers per hour. That's a relentless 200-mile-per-hour jet stream whipping around these perfect sharp corners.
Okay, let's unpack this, because my brain is really struggling with the geometry here. We are taught from a very young age that nature loves chaos.
Right.
Nature loves curves, it loves spirals, it loves the unpredictable messiness of fractals. So how does an atmospheric weather system made entirely of turbulent gas suddenly decide to draw straight lines in space?
It's a great question.
It feels like someone took a cosmic ruler to the top of Saturn.
It completely defies our everyday intuition about how fluid dynamics operate.
Yeah.
So to break down the phenomenon in plain language, the hexagon is essentially a highly structured jet stream made of atmospheric gases.
Okay.
But what makes it truly baffling isn't merely the geometric shape. It's how the shape behaves in relation to the invisible forces of the planet.
There's a timing aspect to it, right?
Exactly. There's this bizarre synchronicity here that actively challenges our understanding of planetary mechanics. The hexagon rotates as a cohesive whole with a period of exactly 10 hours, 39 minutes, and 24 seconds.
And based on the research we've pulled, that specific timing isn't just some random atmospheric speed limit.
No, not at all.
That timing is identical to the rotation period of Saturn's internal radio emissions. These are the Saturn kilometric radiations emanating from deep within its interior.
Yeah, that alignment is the absolute key to this whole thing. Most weather systems on a gas giant get dragged around, sheared by different wind speeds, drifting east or west relative to the planet's core.
Like we see that all the time on Jupiter.
All right, Jupiter's clouds are always sliding past each other. But the hexagon does not shift in longitude. It is locked in place, rotating in perfect harmony with those radio signals coming from the deep, unseen, metallic hydrogen core of the planet.
It's like an old vinyl record player.
Oh, that's a good way to put it.
Like if you think about a record spinning on a turntable, the paper label in the center and the outer edge of the vinyl are turning at the exact same rate.
Yes.
The hexagon is spinning in absolute lockstep with the core, completely refusing to drift relative to the deep interior. And why should you care about this? Because it implies something profound about how planets work.
Yeah, it suggests that the planet's deeply hidden core, thousands of miles beneath the surface, is directly puppeteering its outer atmosphere.
Which is wild. This visible shape is essentially a fingerprint of the invisible mechanics happening at the very heart of the gas giant.
The record player analogy is a brilliant way to conceptualize it. The surface is literally tethered to the depths. And if we trace the timeline of how humanity figured this out, the story gets even richer.
Because it wasn't just discovered overnight.
No. The discovery of the hexagon wasn't a sudden, eureka moment where an astronomer peered through a telescope on a Tuesday night and saw it. Humanity actually flew past this anomaly in 1981 during the Voyager missions.
Wait, so Voyager 1 and 2 captured this?
Yeah, they captured incredible images of Saturn's polar regions, yet the hexagon remained entirely undiscovered in those databanks for years.
So we had the pictures, but we didn't know what we were looking at. I imagine the data from the early 80s wasn't exactly high-definition 4K video.
It was far from it. I mean, the Voyager cameras took a series of disparate, low-contrast snapshots as the probes hurled past the planet.
Right.
It wasn't until 1987 that an atmospheric researcher named David Godfrey took on the painstaking process of piecing together those polar projections.
Just manually stitching them together.
Basically, yeah. He manually assembled and enhanced those various flyby views. It took meticulous analysis of decades-old data to finally realize there was a distinct six-sided pattern hiding in the noise.
So Godfrey spots it in 87, using old photos from 81. Fast forward to the modern era of space exploration, leading into the Cassini-Huygens mission.
Right, which was a massive leap in technology.
Yeah, Cassini arrived at Saturn in 2004 with state-of-the-art cameras and started doing major observations. Yet, reading through the mission logs, Cassini didn't actually get a good, clear, visible light look at the hexagon for years.
Which was so frustrating for the teams involved.
Why was this billion-dollar spacecraft flying blind over the North Pole?
Well, it comes down to the grueling reality of orbital mechanics and Saturn's extreme axial tilt. Saturn takes roughly 29 Earth years to complete a single orbit around the Sun.
29 years.
Yeah, that means its seasons last for over 7 Earth years each. When Cassini arrived in 2004 and began its initial observations, the North Pole was shrouded in the deep, dark, freezing grip of a Saturnian winter.
Oh, wow.
The entire polar region was pitched into years of total darkness.
The sun literally hadn't risen at the North Pole. Cassini was basically trying to photograph a black cat in a dark room.
That is the perfect analogy. During that extended dark period, Cassini had to rely exclusively on its thermal infrared spectrometer.
Okay, so it could see heat.
Exactly. It was sensing the heat signatures radiating from the depths of the storm, rather than visible sunlight reflecting off the clouds.
But the hexagon was still there.
It was. This thermal imaging proved the hexagon was still there, churning away in the dark, and that its structure extended deep into the atmosphere. But it wasn't until January 2009 that the North Pole finally rotated out of the winter shadow and into the sunlight.
I just love thinking about the planetary scientists back on Earth, tapping their fingers for almost 5 years, waiting for the sun to physically rise on Saturn's North Pole.
Just waiting and waiting.
And when it finally did, the visible light footage they captured was spectacular. Cassini was actually able to record high-resolution video of the weather pattern.
And the engineering behind that video was incredible.
Yeah, it was so clever. The spacecraft traveled at the same speed as the planet's rotation, effectively hovering over the area.
Right, maintaining that relative position.
This meant the video recorded only the movement of the hexagon itself, perfectly isolating the internal dynamics of the storm without the whole planet blurring past.
And that continuous, long-term observation afforded by Cassini yielded a massive, surprising detail that no one could have predicted just from the static Voyager snapshots.
Oh yeah, this blew my mind.
Over the course of a few years, the hexagon actually changed color.
Here's where it gets really interesting, because when you look at textbook pictures of gas giants, you tend to think of them as these static, painted backdrops.
Right, just fixed bands of beige and orange.
Exactly. But they are living, breathing atmospheric engines. They have dynamic seasons. They even have localized smog, just like a major city here on Earth.
The seasonal shift is dramatic. Between 2012 and 2016, as Cassini continued to monitor the pole, the entire hexagonal region transitioned from a mostly pale blue color to a distinct golden hue.
Blue to gold. You're talking about an area wider than multiple Earths entirely changing its color palette.
It's hard to fathom.
How does a gas giant generate that much smog?
The primary hypothesis points to a photochemical reaction. As the seasons changed and the North Pole was increasingly exposed to continuous direct sunlight after years of darkness, the ultraviolet light from the sun began reacting violently with the methane gas in the atmosphere.
Okay.
This solar radiation effectively breaks down the methane, causing the molecules to recombine into complex hydrocarbons.
So it's literally baking the atmosphere.
Exactly. This creates a thick, golden photochemical haze, essentially planetary aerosols, that spread across the entire region. The changing colors are a direct visual result of Saturn's atmosphere baking in the summer sun.
So you're saying the UV rays are baking the chemicals in the atmosphere, creating a golden haze, very similar to how Los Angeles gets notoriously smoggy in the intense summer sunlight, just on a cosmic scale.
The underlying mechanism of sunlight driving chemical haze is remarkably similar.
Okay, so we have a massive golden, shape-shifting, six-sided storm that is locked to the planet's deep radio emissions. We know what it looks like, how it changes color, and when we found it. But let's dive into the physics of the geometry, because the why is the most elusive part of the research we reviewed for this deep dive. Like, how does a jet stream make sharp corners?
This is where the fluid dynamics get really fun.
I know there was a fascinating hypothesis developed by researchers at Oxford University who tried to recreate this in a laboratory right here on Earth.
The Oxford Lab hypothesis was a brilliant attempt to physically model the mechanics. The researchers built a circular tank filled with liquid to represent Saturn's atmosphere.
Okay.
And to simulate the different wind speeds on the planet, they rotated the center of the tank and the outer edges of the tank at completely different speeds.
So it's a bit like stirring milk into a cup of coffee, but imagine the spoon in the middle is spinning at a highly controlled, fast speed, and the actual ceramic cup on the outside is spinning at a totally different, slower speed.
The coffee cup is an excellent stand-in for creating what we call a steep latitudinal gradient in the speed of the fluid.
Latitudinal gradient.
Right. In Saturn's case, we're talking about the massive difference in atmospheric wind speeds at different latitudes. In the laboratory tank, this severe difference in speed creates an area of turbulent flow right at the boundary between the fast-moving inner liquid and the slow-moving outer liquid.
And what happened at that boundary?
Well, what emerged in that turbulent boundary was astonishing. The fluid didn't just mix into a chaotic swirl, it reliably organized itself into regular geometric polygons.
Just from spinning liquid at different speeds, you force a fast stream to grind against a slow stream, and geometry pops out.
It's counterintuitive, but yes. Depending on the specific speeds they dialed in, the researchers produced shapes with anywhere from 3 to 8 sides.
Wow.
But the most common shape that naturally formed and stabilized was a six-sided hexagon.
Of course it was.
What happens is that a number of stable vortices, basically smaller, swirling, hurricane-like storms, form on the slower southern side of that fluid boundary. These smaller vortices interact with each other, and because of fluid dynamics, they naturally space themselves out evenly around the perimeter.
I see.
As they space out, their physical presence pushes the main fluid boundary northward, wherever a vortex sits. That regular, evenly spaced pushing gives rise to the straight sides and sharp corners.
So the smaller, slower storms act almost like invisible geometric walls.
Exactly.
They force the main jet stream to navigate around them, ping-ponging the flow into these sharp corners. But I have to push back on this a little bit.
Sure.
Because it sounds a little too neat. If it's really that simple, just a matter of spinning fluids at different speeds, creating these boundaries, then why doesn't Saturn's South Pole have a hexagon?
That is the million-dollar question.
You'd think a spinning ball of gas would be relatively symmetrical.
The South Pole is the ultimate test for this theory. And we know from observations by the Hubble Space Telescope and Cassini that Saturn's South Pole does not have a hexagon.
It doesn't.
It features a massive swirling vortex, but it is completely circular. No straight lines.
Yeah.
The Oxford Lab experiments demonstrated that these polygons simply do not form at wind boundaries unless the parameters for speed differential and fluid viscosity fall within incredibly strict margins.
So it's not just any spinning fluid. The conditions have to be painfully specific.
Very specific.
If the gas is slightly too thick or the wind shears against the neighboring jet stream a fraction too slowly, the geometric walls collapse into a standard circle.
Exactly right.
The North Pole just happens to have the exact right recipe of wind shear and gas thickness, while the South Pole's recipe is just a little too sloppy to build those walls.
The math requires critical thresholds, and that strict mathematical requirement explains why we don't see hexagons at other likely places, like the South Pole. But, and there's a big but here, as elegant as the Oxford tank experiment is, The scientific community is far from settled on it.
There's always a but.
Always. This brings us to the friction surrounding the phenomenon. Other fluid dynamicists have scrutinized those lab studies and pointed out a significant observational discrepancy.
What's the discrepancy?
They argue that the Oxford tank relies on creating what are known as vortex streets, which are a continuous series of distinct spiraling vortices sitting right along the boundary.
And let me guess, when we look at the high-definition video from Cassini, we don't see those spiraling vortex streets lining the hexagon.
We don't. The observational data simply doesn't show the continuous ring of smaller storms that the Oxford model requires to act as those invisible walls.
So what does this all mean? If the Oxford tank is creating these extra spiraling storms that we don't actually see on Saturn, scientists must have looked for a model that doesn't rely on them.
They have.
What are the alternative theories to explain this? Because I know there's more than one.
There are three main alternative theories actively debated in the literature. The first relies on highly advanced computer simulations rather than a physical tank of water. These simulations suggest that a shallow, slow, localized, meandering jet stream, one that is naturally waving back and forth as it flows in the same direction as Saturn's prevailing clouds, can replicate the observed behaviors and boundary stability of the hexagon entirely without needing those problematic vortex streets.
A meandering jet stream makes sense on paper, but a simple, shallow jet stream feels far too fragile to last for decades, or potentially centuries.
It does feel a bit flimsy.
Right. We are talking about a storm that outlasts missions. Is there something deeper anchoring it?
That intuition leads directly into the second, much deeper theory. It involves a concept called deep barotropic instability.
Okay, you just used the phrase deep barotropic instability. You're going to have to translate that for me. What does barotropic actually mean in this context?
Fair point. Think of a barotropic atmosphere as one where the density of the gas depends only on its pressure. In this model, we're assuming there aren't massive, clashing temperature differences driving the flow at that specific depth. And instability in this setup means the flow of the jet stream naturally wants to buckle or wave.
So it wants to wobble.
Yes. If you just have a jet stream trying to flow in a straight line around a rotating sphere, the physics of the planet's rotation will cause that flow to wobble. But here is the critical addition. You cannot just look at the jet stream itself.
You have to look at the big picture.
You have to look at the entire system, which includes the massive North Polar vortex, the NPV, sitting right at the dead center of the pole.
Ah, so the giant circular hurricane spinning right at the literal North Pole is part of the equation.
It is the anchor. Early literature studying just the jet stream alone couldn't make the hexagon mathematically stable. It would always fall apart in simulations.
Because it was too fragile.
Exactly. When scientists modeled the wobbling barotropic instability of the jet stream interacting with that massive central North Polar vortex, the central vortex acted like a dynamic stabilizer.
That's fascinating.
It locked the wobbles of the jet stream into a steady, long-living hexagonal structure exactly akin to what we see.
So it's almost like a spinning top. The central vortex gives the whole surrounding system the gyroscopic stability it needs to maintain those sharp, wobbling corners without tearing itself to pieces.
That's a great way to visualize it.
I also saw some mention in the sources about moist convection, basically water vapor rising and releasing heat, possibly creating that central vortex system in the first place.
The moist convection is likely responsible for generating the storms, but studies suggest the heat release doesn't alter the math of the hexagon's shape itself. The central vortex remains the key stabilizer.
Okay.
Then we have a third major theory to consider, which brings us to a 2020 mathematical study out of Caltech. This study explored a concept called anticyclonic shielding.
Okay, anticyclonic shielding. Let's break that down. A cyclone spins in one direction. Anticyclonic means?
A ring of wind spinning in the exact opposite direction, totally surrounding the main storm.
Got it. A backward spinning ring of wind. So what does a backward spinning ring do to the storms inside it?
It creates what physicists call a vorticity gradient in the background, which leads to a fluid dynamics effect known as beta drift.
Wait, beta drift? I'm picturing a sports car drifting sideways around a corner on a racetrack. Is that what we were talking about here?
Not quite, though the visual of sliding sideways isn't entirely wrong. In planetary physics, beta drift refers to how a spinning vortex naturally pushes itself through a fluid because of the changes in the planet's rotation speed at different latitudes.
Okay.
But when you have neighboring storms that are wrapped in these oppositely spinning anticyclonic winds, their individual drifts interact. they end up repelling each other.
So it is like taking two heavy magnets with the exact same polarity and trying to push them together.
Yes.
They hit this invisible wall of magnetic repulsion and just slide away from each other into a spaced-out, perfectly balanced grid.
That is a phenomenal analogy. The storms push each other away in a perfectly symmetrical manner. Now, Caltech theory is brilliant because it perfectly explains the polygonal storms we see on Jupiter.
Right, the Jupiter grid.
Yeah, Jupiter's poles are covered in clusters of individual cyclones that are trapped in a strict geometric grid precisely because of this mutual anticyclonic rejection.
Uh-huh. So anticyclonic shielding solves the geometry of Jupiter, but does it solve our hexagon on Saturn?
Here is the catch. While the Caltech model is a triumph for Jupiter, it hits a mathematical wall with Saturn.
Let me guess. The scale is off.
You got it. Saturn's polar cyclone does appear to be shielded by opposite winds, but the central storm is simply too big, and the surrounding wind speeds are too slow to hold a polygonal pattern of smaller cyclones like we see on Jupiter. The physics just don't scale right for Saturn's specific planetary dimensions.
So the anticyclonic shielding explains Jupiter's geometry but fails to map onto Saturn. The Oxford tank makes beautiful hexagons, but relies on vortex streets we don't observe. Where does that leave the scientific community?
It leaves us leaning heavily on the second theory we discussed. Deep barotropic instability, where that central north polar vortex stabilizes the deep, wobbling jet streams, remains the most viable explanation for Saturn's sustained hexagon.
The spinning top theory.
Exactly. And I should note, Cassini's measurements of the wind speeds actually preclude shallower instabilities from working, at least during the time Cassini was gathering data. This points heavily to deeply rooted atmospheric mechanics driving the show. But, as with all cutting-edge planetary science, it remains hotly debated. Some researchers still argue for baroclinic instabilities.
And baroclinic would be the opposite of barotropic, so suggesting that massive temperature differences, hot and cold gases fighting each other, are actually the main driver.
Precisely the distinction. The jury is still very much out on whether mechanical spinning or thermal clashing is the ultimate architect of the hexagon.
It is wild to think that we have sent spacecraft billions of miles, spent decades collecting thermal imaging, visible video, and running supercomputer models, and we are still actively debating the fluid dynamics of this one specific shape.
If we connect this to the bigger picture, it highlights the thrilling edge of planetary science. You have this single, persistent shape on a distant gas giant, and its very existence forces researchers to continuously revise our entire understanding of fluid dynamics, atmospheric physics, and planetary evolution.
We think we know everything, and then we don't.
Every time we think we have the math figured out on Earth, Saturn throws a 14,500-kilometer-wide straight ball that sends physicists back to the drawing board.
A straight ball, no curves allowed. And it brings us right back to the tension we started with. We began with a simple geometry puzzle hidden in a blurry 1981 Voyager photograph.
We did.
And over the decades, through the sheer patience of the Cassini mission and the slow turning of Saturn's long, dark winters, that static puzzle has morphed into a golden, shape-shifting, deeply complex mystery.
A mystery that perfectly mirrors the deep, invisible rhythm of the planet.
And that is the provocative thought I want to leave you with today. We look at the top of Saturn and we see weather. We see clouds and photochemical smog and jet streams. But the fact that this massive geometric hexagon perfectly mirrors the timing of Saturn's deep interior radio emissions suggests something incredible.
It's profound, really.
It is. It suggests that to truly understand the weather happening at the very top of the atmosphere, we might eventually have to figure out what is happening thousands of miles beneath the clouds in a metallic core we can never, ever see. The sky is quite literally being written by the core.
That's a beautiful way to put it.
Thanks for listening to People L Pod. Keep tuning in for more stories worth knowing.